Hey guys, and welcome back to Code Case. I finally found the need to record another video, and this one's going to be about data transmission and networks. So basically, data transmission is the process in which data is transferred from one computer system to another computer system. And there are two ways we can achieve this: serial transmission and through parallel transmission. So parallel transmission, as the name suggests, involves multiple bits and bytes transmitted at a single time, through multiple cables. And this is naturally fast, and there is a need to synchronize the data transmission. And because it uses multiple cables, it is expensive, and the length of the parallel transmission cables are pretty short. On the other hand, there is this serial transmission, which is inexpensive and slow, and it doesn't need to be synchronized using synchronizing bytes. So in this, basically, bits and bytes are transmitted sequentially using a single cable. This is used for infrastructure where it has to be cheaper. So for example, home use. And the universal serial bus or USB drive is an excellent example for this. Parallel transmission is used in commercial uses like space observation, medical imaging, etc. So this is about data transmission. Now, while transmitting data from one computer system to another computer system, it is highly likely that there are errors in transmission because of manual data entry, because of humans. Automatic data recording processes might face problems due to obstructions, and there might be data signals which are lost in data transmission. So therefore, for better accuracy, it is required to verify the data entered or received. And this is called error checking, which is achieved by using checksums, validations, and other redundancy checks. So next, we're going to discuss now some methods to check for errors. And the first one up is the parity bit check. So parity bit is an extra bit transmitted with packets. The two computers taking part in data transmission decide upon using odd parity check or even parity check. So while sending the data, the parity bit is set to 1 or 0, depending upon the count of ones in the byte. To set the overall count of ones in the byte to even for even parity protocol, or odd for odd parity check. So when the data is received, the number of ones in the byte is counted, and if it is even for even parity check, then the data is considered to be good. And if it is odd in case of odd parity check, then the data is sent to be good again. So for example, there is this message here which is 1001010. So the number of ones here are 3. There are 3 ones in the byte, and so the parity bit to make the number of ones even should be 1. So now notice that if we add another 1 to this string here, it will be 100101001. And in this case, the count of ones is now 4, which makes the parity even. And then it will successfully pass the even parity check. In case of odd parity check, the number of ones should be odd in the message. So for example, there are 3 ones here, so the parity is already odd, so the parity bit has to be 0, so not to make it even. So this was the parity check, which is widely used for error checking in the modern computer systems. So next we have checksums, cyclic redundancy check, ARQ, which is automatic repeat request, and the check digit. We'll go through them one by one, and then we'll summarize them. So checksums are transmitted at the end of an array of bytes. So the checksum is the modulus of the sum of all of the bytes of the array with a pre-decided number. Now, if this seems a bit hard to you, we're going to work out a simple example here, so don't worry for now. So for example, when the bytes are 52, 21, and 36, now this is the message that needs to be transmitted. and the pre-decided number is 16, then the checksum would be 13 because 52 plus 21 plus 36 is 109 and 109 modulus 16. So note this modulus is the remainder that is received from dividing this number with 16, and that number in this case is going to be 13. So for us, the checksum is 13. So basically, the receiving computer will see if the checksum matches the. It will recalculate the checksum and see if both the calculations of the checksums match. And if it does match, then it is said to be that the data is not faulty. Okay, so the cyclic redundancy check is what's next now. So the cyclic redundancy check appends all the bytes into a single big string that is then divided by a pre-decided number, and the remainder is the CRC checksum. For example, the bytes are 52, 21, and 36, just like the previous example, and the pre-decided number is 16, again like the previous example. Then the CRC would be 8, because 52, 21, 36, this is a big number. When this is divided by 16, the remainder achieved is 8. So the CRC check would be 8. Now, this is a very effective manner for creating and calculating nicer checksums. And so this is a more advanced, so to say, method of calculating and checking for errors. So that was CRC for you. The next thing coming up is the ARQ method. So the ARQ method uses the stop and wait algorithm. This involves sending a packet at a time and waiting until a response of acknowledgement is received from the receiver. If the request is not received till a timeout is reached, which is the TTL, also called time to live, then the datagram is discarded and an error message is sent to the sender. So to make this more simple, suppose there is a sender who is going to send the data to the receiver. So the sender is called Alice and the receiver is Bob. So Alice will send the data to Bob, and it will wait for a particular time till the receiving computer, Bob, sends a certificate of acknowledgement. And unless that is received, it will wait. And that is the stop and wait algorithm. And otherwise, it will send an error message back. And this is the ARQ method, which is very effective for detecting errors and detecting whether the data is transmitted correctly. Finally, we have the check digit. So this method is used in data entry methods like barcode, and one common algorithm in library management is ISBN 13 check digit. So basically, check digit has multiple algorithms. ISBN 13, ISBN 10 are some examples. So one extra bit is calculated and added to the previous digits. So one extra byte actually. And so let's take an example for ISBN 13. This example basically multiplies each digit by 1 and 13 alternatively. So for example, 9780306400615 is a big number, and 9 is multiplied by 1, and then 3, and then 1 and 3. So on, each number is multiplied by either 1 or 3 in an alternative order. And the products, like the multiplied values, are added together, and so this sum is calculated, which in this case is 93, and then the sum is divided by 10 and the remainder is subtracted from 10. So for example, 93 divided by 10 is 9, remainder 3, and then the remainder 3 is subtracted from 10 to give 7. So the check digit here, which is calculated through this algorithm, 7. When this code is scanned, the check digit is recalculated, and if the check digits do match, then the data has been taken in correctly. So this is the need to check for errors solved particularly well, and it can detect a lot of errors like swap digits or um, incorrect digit scanned. And in barcode particularly, this is a very big issue because the codes are scanned incorrectly because of obstructions on the code itself. And so yeah, this is a very effective manner. Now I'm not going to cover the browser and internet server and networks in this video. Maybe some other day we'll pay attention to them. Thank you.